Example 3. Charge on each sphere, an equilibrium problem. Two identical spheres, each of mass 1 gram, hang from a common point using strings of length 10 centimeters. Each string makes an angle of 30 degrees with the vertical. Find the charge on each sphere, G equals 10 meters per second squared. This is a classic G and neat equilibrium problem combining gravity and electrostatics. System setup and free body diagram. In the system diagram, the two charged spheres hang symmetrically. String length is L, angle with vertical is theta, and the separation between the spheres is R equals 2L sine theta. In the free body diagram for one sphere, three forces act: T, the tension along the string, mg, the weight acting straight downward, and phi, the electrostatic repulsion acting horizontally outward. The tension resolves into T sine theta in the horizontal direction and T cosine theta in the vertical direction. Concepts used. First, Coulomb's law, phi equals 1 over 4 pi epsilon naught, times q squared over r squared, both spheres carry the same charge q. Second, force balance at equilibrium. Horizontally, T sine theta equals phi. Vertically, T cosine theta equals mg. Dividing the horizontal equation by the vertical one, we get tan theta equals phi divided by mg. This is the key equilibrium relation. It eliminates tension T completely. Step 1. From the equilibrium condition, phi equals mg tan theta. Step 2. The distance between the two spheres is r equals 2L sine theta. Step 3. Substitute into Coulomb's law. Replace phi with mg tan theta on the left, and r with 2L sine theta on the right. Mg tan theta equals k times q squared, divided by the quantity 2L sine theta, all squared. Step 4. Solve for q. Rearranging. Q equals 2L sine theta, times the square root of mg tan theta over k. Step 5. Now substitute the given values. M equals 1 gram equals 10 to the power minus 3 kilograms. L equals 0.1 meters. Theta equals 30 degrees. K equals 9 times 10 to the 9. After substitution, Q equals 2 times 0.1 times sine 30, times the square root of 10 to the minus 3 times 10 times tan 30, all divided by 9 times 10 to the 9. This evaluates to approximately 8.0 times 10 to the power minus 8 coulombs. Final answer. Q equals 8.0 times 10 to the power minus 8 coulombs, which is the same as 80 nanocoulombs. This is the charge each sphere must carry to remain in equilibrium at an angle of 30 degrees. Note that both spheres carry identical charges, so the answer applies to each one equally. GN neat quick method, very important. Memorize the direct formula. Q equals 2L sine theta, times the square root of mg tan theta divided by k. Ultra fast trick for exam use. For standard values, sine 30 equals 0.5, tan 30 approximately 0.577, mg equals 10 to the minus 2. Direct mental simplification. 10 to the minus 2 divided by 10 to the 9 gives 10 to the minus 11. The square root of 10 to the minus 11 is approximately 10 to the minus 5.5, roughly 10 to the minus 6. Multiplying by L gives the final order. Q is approximately 10 to the minus 7 coulombs. You can write the answer in seconds. Time-saving strategy and the 5 most repeated GN NEET question types. Strategy. Don't fully solve every time, just estimate the power of 10. Always use G equals 10, sine 30 equals 0.5, tan 30 approximately 0.577. Key principle. Electrostatic equilibrium problems equal tension balance plus Coulomb force. Now the 5 repeated types. Type 1. Angle given, find charge. Use the direct formula. This is the most common PYQ type. Type 2. Charge given, find angle. Use tan theta equals kq squared over mg times 2L sine theta all squared. For small angles use sine theta approximately tan theta. Type 3. Medium change, very important for NEET. If placed in a medium of relative permittivity epsilon r, F nu equals F divided by epsilon r. Therefore Q nu equals Q divided by square root of epsilon r. Continuing the top question types. Type 4. Small angle approximation, a G advance favorite. When angle is small, Tan theta approximately equals sin theta approximately equals theta, giving the shortcut theta proportional to q to the power 2 over 3. Type 5. Distance change. If distance doubles, force becomes 1/4. Ultra-fast MCQ tricks. Answer is almost always 10 to the minus 7 to 10 to the minus 8 coulombs. Never solve for T. If mass doubles, Q is proportional to square root M. Same charges repel, opposite attract. Square root of 10 to the minus 10 equals 10 to the minus 5. Curiosity corner for example 3. Did you know that when you pull a woolly sweater over your head and your hair stands out in all directions, that is this exact physics? Every strand gets the same charge, repels every other strand, and finds its own Coulomb equilibrium angle. A Van der Graaf generator charges a metal sphere to thousands of volts. Touch it and your hair literally explodes outward. That is the charge Q and angle theta from this problem, made visible in real life. Thunderclouds build charge through ice crystal collisions. When the charge is so large that Coulomb repulsion can no longer be balanced by gravity, equilibrium fails, and lightning strikes. Even the Apollo astronauts' hair floated upward in the spacecraft from static charge buildup. No humidity to conduct it away, so each strand reached its own Coulomb equilibrium angle in zero gravity. Real-world applications of the equilibrium problem. First, electrostatic spray painting of cars and aircraft. Paint droplets carry the same charge, so they repel each other for perfectly even coverage and are attracted to the grounded vehicle. Engineers calculate the equilibrium charge to optimize spray angle and coating thickness. Second, aerosol inhalers for asthma patients. Drug particles are charged so they repel each other and spread evenly deep into the lungs. The equilibrium charge controls exactly how deep the medicine reaches. Third, electrostatic separators in recycling plants. Crushed plastics acquire different charges and deflect at different equilibrium angles under the same electric force, automatically separating materials without any human sorting. Fourth, crop dusting and pesticide sprayers. Charged droplets repel each other for uniform coverage and are attracted to plant surfaces. Calculating the equilibrium charge minimizes waste and protects crops. This is why physics is not just theory, it feeds nations and saves lives. Excellent work! You have now completed all 3 narrated examples.